Hello, everyone. Hello, everyone. So today we have a guest lecturer. It's Toby, and welcome.
Hello, is this all working?
Yes, we can. Okay. Okay. Yes, I can see you. See you, Toby. I'm going to make you. Host. Okay.
Also, since I'm sharing screen, the one that's F9FCP is my iPad.
So should I make you the host or the iPad the host?
The iPad, because I need to share screen on it.
Okay. Okay, you can still share screen. I mean, if you allow yourself. Okay, let me just change the security settings. Okay, so you can. This is for year 10 and 11.
Yes.
Right. So. Okay, so I've made you host, and you should be able to share your screen.
Yes. Okay. I'll hide you.
Yep.
There we go. That's better. Okay. Should I get started or?
Yeah. Yes, please.
Okay. Thank you. So today we're going to be looking at describing motion, or something that's known as kinematics. So the first thing we're going to need to look at the difference between is distance and displacement. And they're very similar, but they're easy to maybe mix up. So distance is maybe the word you're maybe used to in everyday life, and this is the total amount traveled. Equals total amount traveled. And because this is the total amount traveled, you can go forwards, you can go back on yourself, all of that, and the direction doesn't matter. So this is a scalar. So the direction doesn't matter. So this is a scalar. And then this is in contrast to displacement. Which is a vector. So this is the distance between the start and the end point, but it also has a direction. Because it has a direction, it's a vector. So the difference here, we'll see this in the questions, but traveling 10 miles north is different from traveling 10 miles west, even if they both have a distance of 10 miles. And then to accompany these are words you may have heard before and kind of are used interchangeably quite often in everyday life. And the first one of these is speed. And this is equal to the distance traveled divided by the time taken to get there. And because this is a distance doesn't have a direction, nor does speed. So this is, once again, a scalar. Like the speedometer of a car, that just tells you how fast you're going. It doesn't tell you any particular direction. So the speedometer in a car, that tells you speed. And then finally, velocity. And this is equal to displacement divided by the time taken. And because displacement is a vector, velocity is also a vector. And this means traveling 10 miles an hour north is different from traveling 10 miles an hour west. Or alternatively, if you say run around a racetrack, which is a nice circle, then at the start and the end, you're in the same place. So even though you may have run 400 meters all the way around, your displacement is 0. So even if your speed is kind of 20 miles an hour, 30 miles an hour. Okay, that's a good question. So the difference between a scalar and a vector is the fact that scalars don't have a direction and vectors do. So if we're going back to the racetrack, so if you go right round in a circle and come back to where you started, well, you haven't traveled. So you traveled maybe 400 meters distance, but because you start and end in the same place, you haven't had, your displacement is 0. And so you have a speed of maybe 20 miles an hour, but you have a velocity of 0. Another example is if you're going, say, if you're just running, or sorry, let's go back to the car example. So if you're in a car, the speedometer, when it tells you you're driving at 50 miles an hour on the motorway, 60 miles an hour, it doesn't tell you which direction you're going in. So that's a scale. All it tells you is how fast you're going. But velocity would also be not only how fast you're going, but which direction you're in. And obviously it matters when you're driving that you are going in the right direction as well. Does that clear that up? Okay. Okay. So let's have a look at this. So you're on your way to school and you realize at some point you've dropped your wallet. So you turn back around and look for it. Then you find it and you carry on walking to school. So your journey is summarized like this. And we go in one direction, then we go back. And then we keep going in the same direction as we started. So what is the total distance we traveled? So here, do it here. So for A, so the first bit of the journey, we were going in the direction towards school. So we have 1 kilometer. Then we go back again. And we go back 0.5 kilometer. And then finally, we go back towards school and we go another 1.5 kilometers. So the total distance we had to walk is the 1 kilometer forwards, the 0.5 kilometer back, and then the 1.5 kilometers forwards again. For a total of 3 kilometers. Yes, it should be maybe called a displacement time graph. However, quite often these things are also called distance time graphs, even if they do show displacement. But yes, you're right. Because it goes back, you're right. It is technically displacement, but sometimes they are just still always called distance time graphs. But yes, that is a good point. Okay, so let's look at our average speed. So the next question is, work out your average speed and velocity for the journey. So we see that here we're going forwards, then backwards, and then we go forwards again, but we go faster at the beginning and then slower at the end as we get here. So to work out our speed for this journey, speed equals total distance divided by time, which is equal to 3 kilometers divided by 40 minutes, which is equal to 0.07 kilometers per minute. Now, kilometers per minute really isn't a useful or very commonly used unit of speed. Normally, kilometers per hour is quite common, or meters per second. And in fact, in physics, meters per second is standard. So how do we get from this to meters per second? So there's 1,000 meters in a kilometer. So we times by 1,000 for the meters, for the kilometers to meters. And then we divide by 60 to go from minutes to seconds. So if you have a calculator, you can find it 1.25 meters per second. But we also wanted to work out the average velocity. So the velocity equals displacement divided by time. So the total displacement, so the total distance between your home and school here is 2 kilometers. So we have 2 kilometers divided by, well, the time is still the same. It still took you 40 minutes to get to school. And this gives you a speed of 0.05 kilometers per minute. Or in the nicer units of meters per second is 0.83 meters per second. And now, finally, we want to draw a velocity time graph for the whole journey. So a velocity time graph has velocity on the y-axis and time on the x-axis. Now, this is just going to be a sketch on here. So let's look at some important times so we can mark them on. Well, the whole journey takes 40 minutes. So the maximum time, 40. We'll say time is in minutes. And, well, the velocity when you're looking at a distance time graph, is equal to the gradient of that graph. So the gradient here, to work out the gradient, you do change in y divided by change in x, kind of the y equals mx plus c things you would have seen in maths class. So the gradient is change in y divided by change in x. But here, the change in y is distance. And the change in x is time. So we see that the gradient is just equal to velocity. So let's work out the gradient in each of these sections. So in the first section, the change in y is 1 kilometer, and the change in x is 15 minutes. So we have the velocity equals change in y, which was 1 kilometer, divided by 15 minutes, which gets us 0.067 kilometers per minute. And then for the next section, this section we're going back. So the gradient is going to be negative, which makes sense. We're going back on ourselves. So the change in y is 0.5 kilometer, and the time is 5 minutes. So we have velocity of the second section is minus 0.5 kilometers divided by 5 minutes equals negative 0.1 kilometers per minute. Finally, to work out the gradient of the next two sections, so we see here, because there's a change in the gradient, you start off going faster, and then you slow down. You start off running back to school to catch up time, but then you're tired, so you slow down again. So for the third section, the change in y is 1 kilometer, and the time was 10 minutes. So we have equals 1 kilometer divided by 10 minutes equals 0.1 kilometers per minute. And then finally, for the last one, we went 0.5 kilometer in 10 minutes. So we have 0.5 kilometers divided by 10 minutes, which equals 0.05 kilometers per minute. So let's put these in the graph. So the first section is, let's put it here. This is 0.067. And this is for the first 15 minutes. Then the next section was here minus 0.1. And that was between 15 and 20 minutes. And then the next two sections, so we were at plus 0.1 kilometers per minute between 20 minutes and 30 minutes. And then finally, we dropped down to 0.05 kilometers per minute for the last 10 minutes. So we see that the velocity time graph, it just ends up being the gradient of each section of the distance time graph. Is this making sense? Are there any questions for the first one? Yeah, so when we ask for a velocity time graph, it is just going to be lined. Well, at least in this case, it's just going to be flat lines because for each section, the speed or the velocity is constant. If, however, and we'll see examples later, where if the velocity changes gradually, then the velocity time graph won't just be flat lines. This will be much more connected. We'll see an example of that later. Okay. For the next question, so the next day you decide to cycle. And after school, you and your friend decide to have a cycle race. And your velocity during the race is shown on the following graph. Okay, so we want to work out the total distance you cycled and the total displacement. So how far apart at the start and the end of the race. So distance equals speed times time. And here we've got several different speeds we're traveling at. So we'll need to do each of those individually. So let's look at the first one, this first section here. I'll try using different colors. That might make things nicer. So the velocity is 17 meters per second for this first section. And they travel at this speed, or you travel at this speed for 100 seconds. Times 100 seconds equals 1,700 meters. Something else I'm also going to point out is, if we times the velocity times by the time, this actually gives us the area under this graph. So in the way that velocity is the gradient of a distance time graph, distance is area under a velocity time graph. Okay, let's look at the next section. Well, this is only 10 seconds where you have to turn around. I'm going to do little lines, even though there's not really an area there. This next section, we did 0 meters per second times, 10 seconds. Well, you didn't travel any distance in those 10 seconds. The next section is here. And careful, the speed changes at 250. So we're just going to calculate this section. So that section is, we travel for 140 seconds because it ends at 250 and starts at 110. And we're traveling at, well, after distance, we just need the speed. So we're traveling at 7 meters per second. Oh no, 8 meters per second. So we have 8 meters per second times 140 seconds. And that gets us 1,120 meters. And finally, for this last section, we travel for 30 seconds times, and what's the speed? 20 meters per second. You've really sped up for this last section. And that gets us 600 meters. So the total distance, we have to add all of these up. So we sum these, and we get what have I got written down? 2,820 meters. So that's the total distance you've traveled along this race. But then for B, we want to work out the displacement. So how far is it between the start and the end of the race? So we look at this first section here in red. We see we're traveling in the forwards direction, but then the blue and purple regions we're traveling back. So the total displacement, we do the forwards distance, take away the backwards distances. And this gets us negative 20 meters. And actually, if we look at the resolution of the graph here, the lines are quite thick, the resolution's not amazing. So really, and the whole distance is nearly 3,000 meters. So 20 meters up to some kind of rounding is basically back where you started, which is maybe what you'd expect from a race. So yeah, someone just asked, there's a negative displacement is a negative value. So what that means is, say we're looking at a distance in the forwards direction. So 100 meters forwards, maybe it's better so you can see on the camera, left and right. So we've got 100 meters in my left. There's 100 meters to my right. They're sort of different directions, but if you think about it, going 100 meters to my right is like going negative 100 meters to my left. So whenever you have velocity or displacement, not only do you have to say a direction, but you also have to pick which is positive, which direction is positive. So and therefore going negative, if you have a negative displacement, it means you're going backwards in that direction. So if you travel a negative displacement north, you're actually moving south. Does that make sense? Okay, good. Okay, so the next section we're going to look at is acceleration. So acceleration is the rate at which velocity varies. So acceleration equals change in velocity divided by the time taken. So with this, acceleration is actually a vector. And this can be negative in two different ways. So let's say I'm going 50 miles an hour north in the car, and I slow down to 20 miles an hour in the north direction. So because I've slowed down, the change in velocity is negative, so acceleration will be negative. Sometimes that's called deceleration, but we can just have it negative acceleration. Alternatively, if I want to have a negative acceleration, rather than going forwards in the north direction, I could speed up in the south direction. So if I'm reversing really fast, or reversing and then I speed up reversing, the speed has gone up, but the acceleration, because the velocity's gone from a negative velocity, because we're going backwards, to a bigger negative velocity, because we're still going backwards, acceleration is negative then as well. So one of the questions is, so acceleration have a direction because it's a vector? Yes, or rather it is a vector because it has a direction. And then another thing is, if you're turning, so if you're turning in a direct, so if you're going forwards and you're turning, even if you're staying at the same speed, so your speedometer in your car keeps the same value, as you turn, because your direction is changing, you go from moving north to, hopefully the camera lines up, but east, we see that you've got a negative acceleration in the north direction because you're slowing down, but you've got a positive acceleration in the east direction because you're speeding up in that direction. So accelerations can also happen when you're just changing direction. Okay. Are there any other questions? All right, let's move on to question 3. So we throw a ball up at 15 meters per second. Well, one of the questions is, yeah, so even if you change, so yeah, just changing the direction of travel, that does result in acceleration, yes. So another question, so question 3 is, you have a ball in your hand, you throw it up at 15 meters per second, and it falls down. And so you throw it up at 15 meters per second, it flies up, gravity slows it down, it stops at the top, and it falls back down again. So you catch it, and you don't move your hand, you just throw it straight up and straight down. How long does this take for you to catch it? Well, if it goes up at 15 meters per second, we're going to ignore air resistance and things like that. It's going to, if you throw up at 15 meters per second, by the time you get back down to where you started, it's got the same speed as how it started, but in the opposite direction. So the initial speed, which is often called u, is plus 15 meters per second, because that's how it started. The final speed, or the final velocity, is often given the letter v. It makes sense for velocity. And this is negative 15 meters per second. And this accelerates under gravity. So the acceleration is, well, it's got a magnitude or a size of 9.81 meters per second squared. But gravity acts down. And we've already said, up, throwing things up is positive. So the acceleration is negative 9.81 meters per second squared. And then, so to work out the time taken, we have acceleration equals change in speed. So that's final speed, take away initial speed, divided by the time taken. So we can rearrange this to get the time taken is initial speed minus, final speed minus initial speed. Acceleration. So if we put this in, the final speed is negative 15 meters per second. The initial speed was plus 15 meters a second, but we're taking it away. We have 15 minus 15. And the acceleration was minus 9.81 meters per second squared. So if you put all of this into your calculator, you get 3.1 seconds. If G was 10, we'd get 3 seconds. All questions, yes. 15 meters per second. I was asking, is 15 meters per second the velocity? Yes, 15 meters per second is both the initial velocity, up, and then negative 15 meters per second was the final velocity when we catch it. Are there any other questions? Why is it -2? Ah, yes, that's a good question. Why is the units for acceleration meters per second squared? Why is there's -2 here? So that's a really good question. So the way units work are distance has units of meters or kilometers or something like that. Time has units of seconds. So speed or velocity, it doesn't matter. Because that's equal to distance divided by time, the unit is meters per second, which you can write as meters ms to the -1, where this minus power to the -1 means the reciprocal, so 1 over. And then acceleration is equal to speed divided by time. So it's meters per second, which is equal to meters per second squared. So in other words, your velocity changes by 1 meter per second. And you can rewrite this as ms to the -2, where the -2 means 1 over s squared. Yeah, so when we say -2, it's just the seconds that get squared for the units, not the meter. That was a very good question. Okay, here we've got a graph. So for question 4, we have a graph of height as a function of time. So I forgot to read the question. So you're on a seesaw, and your motion on the seesaw, you go up at the top, then you come back down again, then you come back up again, you go back down again, and you repeat. So we've got a graph here of height divided, or sorry, height as a function or plotted against the amount of time you spent on the seesaw. And you can see that the seesaw kind of starts at 1 meter. It goes up to, 1.7 meters at its maximum. And then when it goes right to the bottom, you're about 30 centimeters off the ground, so about a foot off the ground. Some of you might recognize this as a sine graph, or a sine graph that's been pushed up on the y-axis. But that doesn't matter. If you don't recognize it, that's completely fine as well. So, how do we work out the velocity as a function of time? So, well, we're not really going to be able to do this accurately. In order to do this accurately, you'll need to do something called calculus, which you'll do if you do A-level maths. But the question says sketch. So when it says sketch, we want to get the rough shape right. So what features are important when we're sketching? So the important features are, when is the velocity 0? And the velocity, do you remember we said right in the first question, velocity is gradient, is the gradient of the line. So the gradient is 0. We zoom in a bit. The line is completely flat at the peaks and the troughs. So in all of these sections, velocity is 0. Now, when is velocity at its maximum? So velocity is at a maximum when the gradient or the steepness of is when the gradient of the line is at its steepest. So that happens. The gradient we see is steepest here. Then it gets shallower and shallower and shallower until it gets here. Then it gets steeper again, but in the negative direction. So it's also steep here, but in the opposite direction. So we'll use blue to say it's at its steepest in the positive direction, and green to say steep in the negative direction. So what this means is, if you're on the seesaw, when you're right at the top, you're essentially staying still for that instant you're at the very top. You're going fastest when you're going back through the middle, so back where you originally started. So let's sketch a quick graph of velocity and time. So the first thing I'm going to put on is when this is 0. So when do these occur? 3 seconds, 9 seconds, 15 seconds, 21 seconds, and 27 seconds. So let's plot these on the graph. So that's going to be about here, say 3, 9, 15, 21. This is very uneven, but it's just a sketch. For now, say time is in seconds. So all of the crosses I've put along the x-axis here is when the velocity is 0. And we've already said, so velocity is a maximum for these blue things, for where I've drawn it in blue. So when does that happen? That happens at 0, at 12, and at 24. So it's at a maximum at 0, at 12, which is about here. I'm not going to put on all the numbers. You can if you want to. And at 24, so here. And then where is it negative? Where is it at its maximum velocity, but negative? So that happens at 6, 18, and 30. And also, if we look at this graph, we see it's the same steepness going up as it's going down. So it's the same speed going up and going down. So that means the distance and the velocity, or the speed is going to be the same. So the distance between the x-axis and where we draw these points is going to be the same as the distance between the x-axis and the blue points. So let's plot these green points on. They're at 6, 18, and 30. And finally, we connect these up. And if you do calculus, you'll see that this becomes a cosine graph. But for us, we don't necessarily need to know all of that detail. All we need to know is to be able to draw this, do we see that the velocity changes gradually? And so when we do this, we're going to draw the graph smoothly. You might be tempted to just draw a zigzag, but that's not going to work. We need to draw it smoothly because the velocity in this case varies smoothly. So making sure I go through all of these. This would be much neater if I'd measured all the numbers and made sure they were evenly spaced. But it's just a sketch, it doesn't matter. Now, we can go one step further. And we can try and estimate the maximum velocity. We're not going to get it exactly because we'd need to zoom in on that blue point there. But we can make an estimate. So if we go if we look at the gradient around this little section here, we have the change in velocity here is 0.3. And the time that takes is 1 second. And so, double checking, yes. And so the maximum velocity is about 0.3 meters per second. About. Someone's just asked, why did I pick that very first point? I didn't have to. Well, in order to work out the maximum velocity, I would have had to pick a point around either one of the blue dashes or one of the green dashes. I chose one of the blue because it's positive. You could have done the green and it would have been exactly the same. Then if we zoom in, I see that it roughly lines up with the grid here. Not exactly, but roughly, right? We're just trying to get an estimate. So it roughly lines up with the grid here. So I make a triangle here to work out the gradient. I could have just as easily, I'll choose other colors, done this. I could have done this. I could have done this. For any of these. I just happened to choose one that worked. All of these would work. Okay. Then finally, we want a graph of acceleration against time. Now, my graph is a bit, it's not perfectly drawn. So the accuracy of our acceleration graph isn't going to be amazing. But again, we just want to sketch, just to get a feel for what it's like. So when is the acceleration 0? Well, the acceleration is 0 when the velocity graph, so acceleration is the gradient of a velocity time graph. And so the acceleration is 0 when this velocity time graph is completely flat. And that happens here, 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 and here. And these are the points 0, 6, 12, 18, 24, and 30. So these are all the points acceleration is 0. And then also, when is acceleration a maximum? So that happens when the graph is steepest. And that happens at 9 and 21. And when is acceleration the greatest, but in the negative direction? That happens when the graph is steepest, but going down. So that happens at 3, at 15, and at 27. So if we plot these points, at 9, it will be at a maximum, and at 21, it will be at a maximum. And then at 3, it will be maximum, but negative. Same at 15, and same as 27. And again, notice I've made the red points and the purple points the same distance away from the axis, because you're accelerating in the same magnitude when you're going up as when you're going down. So let's draw this. Again, we're joining up all the points, and everything is going to be nice and smooth in this case. Okay. Does this make sense? This is maybe quite complicated, but really what is important is getting the maximum, the minimum, and the zeros. Whenever you sketch a graph, maximum, minimum, zeros, and kind of whether or not it's smooth or jagged, whether or not there's lots of straight lines or whether or not it's a smooth curve. They're the important features. If you can get some of the numbers, that's even better. Okay. Okay, we are on to our last section, which are called Suvat equations. And these are a set of equations which hold if acceleration is constant, which it often is. The standard example is when you throw something in the air, acceleration is constant. It's always 9.81 meters per second squared downwards. So whenever you're throwing stuff in the air, acceleration is constant, it's constant down, and these equations hold. But there are, of course, other cases as well. Gravity is not the only case. And we've seen a few of them. So we've seen the definition of velocity, we've seen acceleration, but there's a few more complicated ones. I'm not necessarily going to prove them right now. If there's a bit of time at the end, we can have a look at it. And I think they're shown on the kind of sheets you're given. Some of them are proven on there. So I'll just recap them here. So firstly, you need to know what the symbols mean. V always means final velocity. U means initial velocity. T is time. A is acceleration. And finally, S. I don't know why it's S, but this is displacement. I have no idea why it's an S. I guess Sue, that sounds quite nice when you use all of these letters, but I really don't know the reason. So the extra equations we have is V squared equals U squared plus 2AS. So this is useful if you want to know what the final speed is. If something's been accelerated over a distance, you don't necessarily know for how long, but you know the distance over which it gets accelerated. The other one is displacement equals a half a t squared plus u p. So this is if you start off at a speed and accelerate for a given length of time. This is the distance you will travel. And then finally, so someone's just on what are these equations for? These equations relate velocity, distance, acceleration, and time. Whenever you have constant acceleration. So I'll put the final one in as well. So displacement can also be given as final plus initial velocity divided by 2 times time. And these hold whenever we have constant acceleration. Okay. Are there any questions before we move on and have a go at some problems of our own? Okay. Okay, so question 5 is, in your heart, I don't know if you've seen these in biology, but you have kind of 4 different compartments. And in one of them, called the left ventricle, blood is accelerated from rest. So it starts off at rest, and it's accelerated to 30 centimeters per second. And this is done in a distance of 1.8 centimeters. So your heart's kind of about this big, that little part of your heart. So we're after, what is the acceleration of the blood? So let's have a look. Well, what do we know? We know the displacement, so the distance over which it gets accelerated, is 1.8. The initial velocity is 0. The final velocity is 30 centimeters per second. And the thing we want to work out is A. So let's look. Which of these equations has V, U, S, and A in it? And we see that it's this first one here. The other two have time in them. We're not after time, or at least not yet. So we have V squared equals U squared plus 2AS. Well, we know U squared is 0, so we can cross that out. And we can rearrange for A. So we have A equals V squared over 2S, which if we put numbers in, we have 30 centimeters per second, all squared, over 2 times 1.8 centimeters. We should get, if I typed everything incorrectly, 250 centimeters per second squared. So this is the acceleration of the blood in your heart. Now let's look at how long this takes. So we have acceleration now. So we could use the second equation. We have the displacement, which was 1.8. We have the acceleration now. So we could use the second equation. However, I'm not going to. Partly because, well, may have calculated A wrong in an exam. So there's no point using it. If we can work this out without using A, may as well, just in case we made a mistake. Also, there's a t squared in it, and square rooting things adds a whole nother step. So we're going to use this third equation here. So we have S equals U plus V over 2 times T. So we can rearrange this to get T equals V over 2S. Remember, U was 0, so we can cross it out. So when we put all these in, oh, sorry, it should be 2S over V. Which if we put numbers in, we get 2 times 1.8 centimeters over 30 centimeters per second, which gets us 0.12 seconds. Now, does this seem reasonable? I mean, a heartbeat, if you're resting about a second, if you're exercising, maybe it takes half a second, and multiple processes have to go on in that time. So this is the only thing that happens. It has to go in the different sections, it has to be pumped to the lungs and then pumped, then goes back and then pumps out again. So considering a heart is about half a second to a second to get all of those processes done, 0.1 second maybe seems quite reasonable for that acceleration to happen. And then finally, the last question. We have a 250-meter high cliff at a national park. I'll draw this as I read it. And a boulder breaks loose from the top. At the bottom, there's a tourist. How much time does this tourist have to get out of the way? So we're told they have a reaction time. People have a reaction time of about 0.3 seconds. We're given the speed of sound, and we're also told the height of this is 250 meters. So let's have a look. How much time do they have to get out of the way? So they have to wait to hear it. So how long does it take for the sound to reach them? So the time for the sound equals the 250 meters divided by the 335 meters per second for the speed of sound. And that takes 0.75 seconds. Now, how long does the boulder take to reach the bottom? That's what we want to know. So we're given the distance. We know the acceleration is due to gravity, and that's a constant. So we can use one of our Suvat equations. What we have is distance and acceleration, and we want time. So what we're going to use is this second equation. Note that u, so the initial velocity, is just broken loose, so u will be 0. So the equation we need is S equals a half a t squared, which gives us t equals the square root of 2s over a. Okay, so what? Let's plug numbers into this. So the time is 2 times the displacement, so the distance it has to travel is 250 meters, divided by the acceleration, which we said above was 9.81 meters per second squared. And if we put all of that into our calculator, we should get 7.1 seconds. This is how long it takes the boulder to fall. So, how long does the tourist have to jump out of the way? So, there's the 7.1 seconds it takes to fall, but we have to take away the sound, the time it takes for the sound to reach them, so that's 0.75 seconds. But also, they don't react instantly. We're told they have a reaction time of 0.3 seconds. So we have to take that off as well. So if we do this, we should end up with 6.05 seconds. They have about 6 seconds to get out of the way. Not a huge amount of time, but maybe doable. Are there any final questions? That's the last question I have written up and planned. So are there any questions from you? Okay. Okay, well, people seem to be saying no, so I mean, there's about kind of 15, 20 minutes left. So if there's anything else you want me to go through, I can. But if not, then I think you're free to go and you can have a nice evening. Okay.